Gernot, I think we can start. I don't know if is there anyone else coming?
No. Sorry.
So I think we can start.
Okay, so good morning, everybody. I would like to first bring up the question of break again. I was asked to ask.
Do you want?
So maybe we shall make a short break, a few minutes after 1 hour. Just you can go to the loo, have some water, a coffee, and then. Okay. So please remind me. I will try to find a good point to stop for. Okay, perfect. So I would like to recap a little bit what we did yesterday and also what the plan is for today. So yesterday I gave you, first of all, I gave you an overview of at least part of the applications of random matrices, and then I introduced 10 classes which I motivated by certain symmetry properties of Hamiltonian and Dirac operators, and I, at least for some of these models, I computed the joint density. So if we go from the matrix to the eigenvalues, let's say lambda 1, lambda n, we then convince ourselves that the partition function is always of this form that okay, we have to integrate over all the eigenvalues. Then we have here a weight function. This is for the non-Gaussian case. We have Van der Waals determinant, so the products of the differences to the power beta. And then here we may or we may not have some factor with some power alpha, and the integral here is either over r or over r plus. And this alpha took some special values for 7 of these classes. So this is, if you like, the starting point for spectral analysis, and I also try to convey the message that what we are doing is we are typically not starting from first principles, but we do a kind of statistical mechanics approach to spectra of a used class of operators. Now, the next step we then did was still on the board, so I didn't have to raise much. So I convinced you that after doing an appropriate rescaling, we have a factor of n here, and then we can do a saddle point analysis. And the outcome of the saddle point analysis was that the saddle point, so if we put everything in the action, so there's differences we'll get here, they will give a logarithm. We disregarded this for the time being. And so then we look for the derivative of the action, and so the action was defined when going from the sum here over the lambda I to an integral. So this was kind of the action that also led us to the point that the partition function is actually can be written as e to the something n squared times something of order 1. And this object we will call free energy. And this object is then given by this equation here, given that rho star is a solution to this saddle point equation. Okay, so yeah, the saddle point equation was what we got here. I mean, and the pole we got from differentiating the logarithm that came from here. Okay, so in principle, we would now like to go about and compute not only the free energy to leading order, but maybe also compute corrections. And I will motivate that these will give important information in application to two-dimensional quantum gravity. But the framework I will use for that is not this one using saddle point methods, because basically
Sorry, but this contribution, the physical point of view, from the physical point of view, are thermal fluctuation or something like this, right? In some sense, yes. If you like, if you think about it as a Coulomb gas, and you have a temperature beta. However, as I will show right now, these higher order contributions also have a completely different interpretation in terms of counting Riemann surfaces for quantum gravity. Okay. So the aspect of fluctuations will also come, but that will come later, so I have to ask you to be patient. Other questions? Okay, so I was saying something about 2D gravity, quantum gravity. So let's start with classical gravity, so the Einstein-Hilbert action. Would look as follows.
So we have a metric, G mu, that depends on x, of course. And then we have here some coupling constants, Newton's constant, we have a Ricci scalar, and let me also add cosmological constant here. Okay, now I'm looking at this in 2 dimensions. Now in 2 dimensions, there's an important difference to 4 dimensions, namely that manifolds, or compact manifolds, call it M, they can be completely classified. Namely, they are classified according to their genus. G. That can take integer values, and what the genus counts is basically just the number of holes in M. So this is genus 0, that's just a sphere. Then we have the torus. It's genus 1. And I mean, in general, the surface will have G holes. Okay. And the other thing that characterizes this manifold is the area. Let's call it A. So a manifold we will then label by its genus G and its area A. Okay. Probably the reason why you have not used this action so much is that this is topological. So this does not really give you propagating degrees of freedom, but okay, we like simple models that we can solve exactly. So let's stick to that. So so the action topological, and this also I think goes under the name of Gauss-Bonnet theorem. So S is given by the following quantities: minus 1 over G Newton times 2 minus 2G plus lambda times L. So this is kind of clear. I mean, this just gives you just the area times lambda. And this 2 minus 2G, also called chi. This is order characteristic. Okay. Now this action still has some properties. Under different morphisms. So, in a naive approach, we could now say, okay, let's just write down this classical theory and then define a path integral over that, and that will give us a quantity theory. So let me write down what that is. Please, in a formal way. And then, because this is an introduction to matrix models, we have to make matrix models appear somewhere to be able to compute this. Okay, so how would that look like? Well, that will look as follows. So we have a partition function. Let's call it the quantum gravity that depends on two couplings. And it has the metric here as a dynamical field. So we will have to integrate over the metric. let me write this as this. So this is the path integral, so we integrate over our possible path, and we have to normalize this by volume of diffeomorphisms times e to the minus s. Okay, now I said that we can, because this is, if you like, a sum over all possible manifolds, we can now write this as a sum over genus and an integral over the area. Okay. So all areas are allowed, all genus are allowed. Then I just put in the action here, this. So e to the minus s is this. So e to the plus 1 over chi minus a. And then we are still left over this integral u, where we integrate over manifold. Okay, and it's this integral that is difficult. Okay. Now there are two possibilities to go forward. One is a continuum approach. That I will not take, and this is of course under the name of theory. What I would like to do is I would like to use a discrete approach. And so what we will do is the following. Well, here I put this as a reflex, so you see that this is two-dimensional. Now I can use that also for another purpose. So what we will do is we will say, okay, we will regularize this sum over manifolds by discretizing our surfaces. Okay, so we will just make a triangulation. Here I do a triangulation with squares. Okay, and these triangulations we will generate by using matrix models. Okay, so triangulate surface. And what we will use for that are finite diagrams. Of matrix models. And you can already see where we only want to have sums of our connected diagrams, so we will then probably look at the free energy of this of the matrix model. Okay, because if we have not the path integral here, but we have a matrix model, I will have to explain what the finite diagrams are. I will do that, of course. So then the connected ones will be generated by the free energy. Okay. Now you could say, okay, why does he talk about matrix models? Can we not just use a scalar field theory? And then this will, okay, we will have propagators, we will have vertices, and then you can imagine that with these we can do some, okay, this we can do as a final diagram. That's of course not very interesting as a triangulation, but you can imagine that if you add more of these, that this will give you a triangulation of the surface, and when this is a closed diagram, that can approximate the sphere if it has no hole, or a torus when it has a hole, etc. Now, the reason why this has not pursued is twofold. One is that
this does not have enough structure. And well, you didn't ask a question here, why are these all? I mean, in fact, I could also draw other surfaces that are not orientable, and it turns out that some matrix models will count orientable surfaces and others will count also non-orientable surfaces. I think the most popular non-orientable surface is the Möbius strip. Okay, I think you all know how this goes. So you go around once and then there's no outer side and no inner side, but there's also a kind of version which is called blind spotted. So you have to think that this goes in here and it comes out there. So this is a two-dimensional surface that is a bit difficult to think about, that this also does not have a orientation. So, using this scalar field theory, we will not be able to, from the final diagram, to see that we have an inside and an outside, but we want to have it so that we can distinguish these from those. And the second reason is that the scalar field theories are very difficult to sum. I mean, the idea is clear, no? I mean, I will have to do perturbation theory in alpha, and I will make that more precise. But I mean, for every vertex, you get an alpha, and at the end, you have to sum up these perturbative expansions. So. Fast. And if you want to read more about this, there's an article by Ed Witten from 91 actually, where he explains this much better and more detail I can do now. And this is called 2D gravity and intersection theory on modular surfaces. I think if you Google it, you can also download it for free. Well, okay, so what we have to do is now we have to use matrix models, and I have to explain the final diagrams of matrix models.
Sorry, I didn't get the part of it, not enough structure. Could you explain it again, please?
Yes, maybe it will also become clearer when I draw the diagrams for the random matrices. So for the random matrices, we have double line Feynman diagrams, and then we will have arrows, and then the plaquette will have an orientation. Okay. Okay. And that orientation, if you like, is like an arrow that points out, and so we can decide on that final diagram that it has an outside and an inside. And because this diagram has an outside and an inside, it will only generate orientable surfaces. Whereas here, we cannot necessarily do that. So this would generate orientable and non-orientable surfaces. Other questions? Okay, so let's try a matrix model, and we already know matrix models. So let me write this down. So we have Hermitian model, trace h squared minus from h4, and I think I put here half for normalization. So the matrix is Hermitian. n times n, and invariant and unitary transformations. So it's, if you like, a UN H theory. But it does not have a kinetic term. So the Feynman rules are very simple. I mean, the propagator is just what we get from this, and then we get a vertex from this. And then we can glue diagrams together, and we can actually write down what they are. I mean, so let's see. So we will use this double line notation for that Vogt introduced. So we will write a propagator. Let's call that P. The following way. J, K, L. And we put arrows here. So this corresponds just to the contraction Hij, H, K, L. And this will just give us a factor of 1 over n delta I K delta J L. Okay. I hope everything is clear. I mean, just a constant. I mean, in contrast to when you have, scalar field theory, you have 1 over p squared, etc. So, this is one ingredient, then we have a vertex. Let's call it V. This looks as follows. And then we put the lines going in and out, such that they always go in opposite directions. And for a vertex, we get a factor minus alpha n from here. And then we still have loops. Let's call it L. And whenever we have a loop, what does that mean? Well, that means that we contract all the indices that run around in this loop here, okay? And that means we sum over the indices, and the indices run from 1 to n, so we get a factor of n. Okay? So now I can write down explicitly the contribution of any graph. So the graph will have v vertices. So from every vertex we get minus alpha v. Then from every graph we have p propagators. That gives our minus 1 propagator. So p is the number, then v is the number of vertices, and L is the number of vertices. Okay, yeah. I hope this is clear from the notation. And then for loops, I get again a plus n. So if I have L loops, I get this number. Now, already Euler knew about graphs that this number here, this combination, is just the Euler character. So this is 2 minus 2, 3, which is chi. Okay, so now, what was the goal? We wanted to, well, we know already about these matrix models. We have this relation, so, well, I think you know from your quantum field theory that the connected graphs are generated by F rather than by Z. So we will have to look at F. And so let me write down what F is. F will be the following sum. So this is okay. I will keep some more space. So F is a function of n and of alpha.
and then we have to make a matching between alpha and n and these couplings. If we want to use this discretized theory here to marry it with this theory. This is the next step to be done. Okay. So we have so in the matrix model, we have n alpha. This is given by the following expansion. I mean, let me separate it in this way. This square into the minus 2g. And then we have, I will write it the other way around here, as g, and this we can also write as into the 2 minus 2g, sum over k to infinity, minus alpha k f k. Okay, so this is g. And I was telling that, well, this is, if you like the turbo, we cut this up to some order in perturbation theory. And our goal will be to compute these FGs here non-perturbatively, so to all orders in alpha. So this is what we know. Okay, this is just an ansatz. We say that this will have an expansion 1 over n squared. As we can see here. And then we split it up in this fashion. Okay. So let us now make a comparison. So I should have written this underneath. So what do we have? Here we have, so this here is e to the gn minus 1 to the 2 minus 2g. So we will have to identify this with, sorry, I need one more step. This is true, what I've written down here. But I would like to do one more step. This is still continuous surfaces, okay? But what we want to do is we want to approximate these tori, spheres, etc. by discretized surfaces. So let us write it as surfaces of size with plaquettes of size epsilon. So the area will be k times epsilon of size epsilon. Okay, and then, well, you just write this in here, and then you can write this as follows. So that implies, maybe now I can write this one on top of each other. So we have a sum over genus. Then we have a sum over k. E to the minus lambda epsilon to the power k. Okay. This is just minus lambda epsilon k, and that's minus lambda a. Okay, and the areas are now discretized, so we will have areas of size epsilon, 2 epsilon, 3 epsilon, etc. So this sum here has replaced this integral and this part. Okay. This I write out into the plus g inverse to the power 2 minus 2g. Okay, and then we still have this integral, but now discretized. Okay. So you see now, if we do the following identification, then g minus 1 minus alpha and e to the minus epsilon lambda. And this integral here, fgk, so if we are able to count these, or to even count these two together here, as we do here, then we are in business for our discretized theorem. Okay, so there's one more thing I have to tell, namely the way this identification is then realized on the Feynman diagrams. I think I should erase this now, so this you have understood. Okay, so let me draw a Feynman diagram. I hope you don't mind that I leave out the errors for the moment. Okay. So this is what we would generate with the Feynman rules that I have just erased. Now, my claim is that the discretized random surface is actually the dual graph to this Feynman diagram. So let's put here a dual graph. Okay. So what was a vertex before now becomes a plaquette. Why do I do that? Because the vertices are counted by minus alpha. And the plaquettes are counted with this. Okay? That's why I have to do this identification. So this identification just means that, okay, propagators go to propagators because this is a propagator and this is a propagator, so we identify propagators go to propagators, vertices go to loops, and loops go to vertices. Okay? So, what we will do now is, our aim is solve the matrix model at genus 0 first, and then a higher order, so we want to compute limit f n goes to infinity, f naught, and then tomorrow we will actually come to genus 1 plus order 1 times 4. Okay, so this is why this lower order contribution is interesting, because this will just give us this free energy correction to the leading free energy will tell us about surfaces with one hole. Okay. Now, there's one thing, of course, in this limit that I would like you to think about, also because I would like to make contact with some other lectures, is that now, if this is as it is, when n goes to infinity, planar diagrams, so planar diagrams are diagrams you can put on a plane, and these are, of course, equivalent to the diagrams you can draw on the circle, on the sphere. Always dominant. Aha, but I mean, we just set up this whole expansion to learn also something about higher genus contributions. So how can we get something like that?
because at the end of the day, we want to make our discrete approximation to become a continuum. So what we will need is that we will have to have that, well, we need to find some critical behavior. So that Fg will blow up to compensate this, so that the whole combination will give a contribution. Okay? With some power, and I think I can write this down already. And here will come some words, 3 minus gamma string 2. This is of course a convention how I call these exponents. Okay, and this is string susceptibility. Okay, what I'm saying now will hopefully make more sense when you've started lectures on conformal field theory. But since I'm not here next week, so this comes out of Liebel, and the C is the central charge. And that appears in another object, which is called the solar algebra. So we have a commutator relation. Plus okay. So yes, these are all words. So let me try to fill these words a little bit. So apparently there is a relation between our matrix model and conformal field theory that will hopefully become apparent a bit more, where these notations come from. Now I can say a little bit what this Virasoro algebra is. This is an algebra of generators of conformal transformations. Now I hope you will see next week that conformal transformations, which are angle-preserving transformations, they have the property that in 2 dimensions the algebra becomes infinite dimensional. So what happens in 2D actually, if you go from your coordinates x and t to complex coordinates, so to x and t to z and z bar, that conformal transformations are all coordinate transformations that I cannot derive that now. Let's send f z into some meromorphic function of z and z bar into some other. So if you write this as 1 plus some and z with some coefficients, put the right coefficient here. And plus 1, then the following objects will be the generators of these transformations. Okay, now you can check that these objects here, which are the generators for such transformations, satisfy this algebra without this central extension. Okay, so that is the relation. Once we have a critical behavior in our free energy to conformal field theory. Now, another thing that we will show is that that
our matrix model has the following property. The generators acting on the partition function will be 0 or n equal -1. This is something I will derive. So you see, this you will, it's not long, but I mean, you have to do something. You have to define what is a conformal transformation, get the equations, then do some gymnastics, you will get some Cauchy-Riemann equations, and then you see that you have this symmetry here. I think this is clear that these are the infinitesimal generators, then this follows, and our matrix model will have this property. So there is definitely a link. So let me go back and try to translate what this behavior here, this critical behavior, will correspond to, and what. So what is the signature of this? We will have to look at in matrix models, and I will also explain to you why this has something to do with a continuum limit. Okay. So I think the best is to give an example. So I said, okay, this relation that comes from this funny thing, Liouville theory. So let's see what we get if we take the simplest value. Well, let's put c equal to 0. Okay? Because that's also where we honestly could verify this, because this was not there. So for c equal to 0, if you put that in here, you get square root of 5, that's square root of 25, that's 5, so you get minus 6 over 12, so that is minus a half. And that is called pure gravity. That is maybe not so surprising because we started with an action that has nothing but surfaces. So what will happen then? So this critical behavior in general minus will look as follows. So I said we have to tune our quartic coupling to some critical value, and alpha critical. So what does that do on the density of eigenvalues? Now for
sorry?
Yes.
You have this for c equals 0, gamma equal -1/2, and this is square root of 25 then.
No, minus. Yes. We have this term.
Yeah, this is 0, -1, minus.
Square root of 25 is 5. -1 minus 5 is 1.
Ah, sorry. Yeah, I'm stupid.
No, it's early in the morning. Okay, and the other ones, they are actually, okay, let me write this down. They are done for, okay, C equals probably, so if you put this, you get this. And these PQ integers that label the central charges in the Pro algebra, you will hopefully see next week. So, back to matrix models. You remember we had the semicircular density that was for the Gaussian. Now we have switched on our quartic term, so obviously this will change. We'll compute that later today how this will change. Now if we tune our coupling So the critical behavior, what happens? What happens is that that was the square root, so lambda minus a minus 1/2 at criticality will vanish like 3/2, or like 5/2, or 7/2. And this critical behavior will translate into the free energy to show this critical behavior at all higher orders. This is how we will see that in the matrix model, and I will not, since the best we can do in this week is to get to F1, okay? And then I will give you some hints how you can calculate that this indeed happens for criticality. But this is how the relation is for criticality. Okay. Now one last thing is that we have to convince ourselves about is that this critical behavior has a relation to a continuum limit. By continuum limit, I think intuitively you know what it should be. I mean, we make our plaquettes smaller and smaller so that this triangulation generated by finite diagrams gets finer and finer and becomes a continuous surface at the end. Okay, so this should have somehow epsilon going to 0. Okay? Remember, epsilon was the size of our plaquettes, the area was greater than epsilon. So how do we see that? Well, we see that here.
One question.
Yes.
About the diffeomorphism invariance. In this discretization, what happens to the diffeomorphism the discretization?
Well, you break it completely by a discretizing surface. Yes. Okay, you still have the lattice
But
version
it
if you like.
remains some symmetry.
Well, in the continuum.
It remains a sign of diffeomorphism invariance.
Well, the philosophy is the following. We cannot, or at least I cannot calculate this integral. So what I do, I just discretize my surfaces and hope that then I can do the counting. Okay? At the end, what we are doing here now is just counting finite diagrams, very simple ones. And then I hope that with this procedure, I can then take a continuum limit and give a meaning to this integral that I cannot compute otherwise.
But then you require diffeomorphism invariance in the continuum limit.
Yes, I should, yes. But of course the problem is that we have to divide by the volume of some of this infinite dimension 2, and I don't know how to do that. That's why we do this. But of course in the continuum limit we should recover it. As we should recover the Einstein-Hilbert action.
And another question,
yes.
for why the name of
Well, because well, I'm not answering your question, but I mean, if you have higher exponents, this will be gravity coupled to something. So, for example, spins sitting on the surface that are some extra degree of freedom, and they are absent when in the simplest case, the spin degrees of freedom. That's why it's called pure gravity.
Okay, so the polarization, you mean the polarization?
Well, I mean, really matter degrees of freedom that sit on your random surface. So, just naively you would say, okay, our quantum gravity is just sum over these spheres, torus, etc.
Okay.
Now we want something more complicated, so let's put some spins on the surface. There's some extra degrees of freedom. And that is what corresponds to this. I mean, this is all very sketchy. If you want to know more, please have a look in this review by Ginsparg, Justin, and Francesco. But I thought it's important to have this in a way in mind when you go to the conformity theory class next week, where okay, the beginning will be probably completely different. This will of course appear, and then you will also see these more complicated conformal field theories, and then you should remember that matrix models have something to do with them, and that in matrix models we can actually compute something. We can compute some objects like the free energy in these setups. I should also say that the one matrix model that we are studying will only give rise to these exponents here. And if you want to do all P comma Q, you have to do two matrix models, and that's something I will not do in this course. I can tell you what it is, but not much more.
Sorry, another question?
Yes?
As far as I know, if you give mass to the graviton and then take the limit to 0, you don't get the same result as if you take the mass equals 0. How do you know that taking this limit you will get the same result?
Well, a priori, I don't know, but I mean, you would have to find that we have introduced the mass term in our discretization, and this I don't see at the moment.
No, it's an example of that the limits
I
are not the same.
Yes. Well, I think you see it because you see that you get the same critical behavior as in the continuum version where you don't discretize and you don't add, extra terms. So, but just by comparing to Liouville theory, in case you can compare. Okay, so let's go back. The idea was that we have, and then f was at 0 plus 1 over n squared at y plus. And we wanted to make these guys contribute. So in order to have that happening, we have, in case I don't have the wrong sign here, which I think I do, so we need that the following combination has to be finite. When alpha n goes to infinity and alpha goes to alpha infinity. So I think there should be a minus sign here somewhere, because otherwise, so when gamma string is 1/2, then this is 3/2. Sorry, it was minus 1/2, so this is 5/2, so this is positive, so this should be negative. So I think because this also comes with chi, so I think, no, I think it's correct. The combination, so we get, in general, we have some. Yes, and if this goes like this, then yes, okay. So this limit here is called double scaling limit. Or just DSL. And I said that I wanted to convince you that this has something to do with a continuum limit. So let's look at the following object. So let's look at the expectation value of the area in the matrix model. So that would be like k times epsilon. Okay, now I think it's no longer written down, but you remember that fg we wrote as the sum over k minus alpha to the k. So if we differentiate fg with respect to alpha, we will bring down the k. And if we again multiply with alpha, we restore it. So we just generate this k as follows, alpha in alpha fg. Okay. And then if this has a critical behavior, this will go as follows, epsilon divided by alpha minus critical. So you see that when alpha goes to alpha critical, this goes to 0. So in order to get an expectation value for this object to be non-zero, we also have to have epsilon going to 0 when alpha goes to alpha critical. So in that sense, yes, we do have a continuum limit when we have this critical value. Okay. Now, one last thing, and then maybe it's a good point to make a break. All I've done here was using squares for our triangulation. Okay? Now you can ask, of course, why did I pick squares? Well, why? Because they are easy to draw. And we have seen already this random matrix model, but why did I not add h to the 6th term? And the answer is yes, of course you can do it. And you can add more terms. Now, what you expect in a reasonable theory to happen is that it doesn't matter if you use squares or triangles or hexagons in your triangulation, the continuum limit should give the same answer. And that, in this setting, is the notion of universality. So it doesn't matter what kind of potential you do, you use it to generate triangulations, but in the continuum limit, your choice of triangulation should not matter. And that, in some sense, gives you what is called universality. So an independence of the potential. Remember, the potential was the probability distribution for the matrix elements. By the way, they are now coupled. If we have trace H4, they are no longer independent. But we have some freedom in choice, and we expect that if matrix models are nice, something universal should come out, and it does. And this is something I will show. So let's have a break now for 5 minutes.
5 minutes, yeah. Yes, yeah.
Let's continue. Okay, so we are now back. Yes, please.
When you write beta, I'm not sure. Beta 1 is we are elements of the matrix,
Yes.
beta 2 complex, and
Yes.
beta 4 quaternion.
Yes.
Okay.
Some people use different conventions, unfortunately. There are some papers by Bertrand and Nard where they, I think, divide beta that I have by 2. But I mean, our beta is very simple. It counts the number of degrees of freedom for matrix elements. So complex means 2. Okay. Now what I will do is I will now present the method of loop equations to compute higher genus contributions. Now you may of course ask, what about other betas? Now the other betas indeed correspond to non-orientable surfaces. I have a reference in here. Then there are solutions of loop equations for real beta. This is some modern development that I will not cover, for example, by Bertrand Nard and Nicolas Vantin. I also have a reference here. And the last word about mathematics. We did this, physics, hand-waving, Feynman diagram, reasoning that the free energy has an expansion in 1 over n squared. Well, this is of course not wrong. I just wanted to point out that there has been also rigorous work by mathematicians Gaetan Borot and Alice Guillaumet. They have proven that this expansion is indeed true. And they've also looked at more complicated cases where I will allude to later. And again, there's a reference in the notes. I don't want to write all these references to lose time. Okay, so let me record some definitions because we will need them later. So we will now use potentials that contain arbitrary number of couplings. So H is again Hermitian. Complex n by n. And we will need all these couplings to generate all moments. And at the end of the calculation, we may set many of the couplings to 0 to have just an example and compute, let's say, the density for a quartic model. But for the time being, I will need all terms as sources. Okay. You remember that the partition function was e to the n squared f, and this was given by the matrix model integral e to the minus n trace h. So from these sources, we can compute all moments. 1 over n trace h to the j simply by, I mean, it's clear what the expectation value is. No, I just put the trace h to the j. So it's h to the power j, and then taking the trace. Or I put that in here and divide by the position function. That's the expectation value. So this I can, of course, generate by the following differentiation. d over d j, no sum over j of f. Okay, so this is just minus j j of ln z over n square. I mean, you need the ln to get the expectation value. You divide by n square, and then, well, the differentiation will bring down an n, so the n cancels one of the n's, and then in the potential you get this. I mean, it's clear, no? This generates all the moments. Now we will need all moments because we want to get the resolvent. P, which is 1 over n, is 1 over n minus h. So this will be our central object, and we can also write this as 1 over n sum j from 0 to infinity trace h over j divided by p to the j plus 1. Okay? We just expanded the geometric series, nothing special. Now, we already argued that f has a genus expansion. And consequently, we will also assume that the genus expansion can be resolved into the minus g w g. Okay. Now, there's another object that we will need. That is the connected two-point resolvent, because this will appear in the equation that we will derive for this object. So this is our central object, and the equation that is called loop equation will be an equation that contains W and that can be solved iteratively to solve first the genus 0 in the leading order, then genus 1, genus 2, etc. So connected two-point resolvent. So that is given as follows: P1, P2, which is no n here, trace 1 over P1 minus h, trace 1 over P2 minus h, minus the same thing but factorized. Now, why do we do that? We do that because we expect that in the large n limit, these objects will factorize. Okay, so that this object will give us the interesting behavior. If I don't subtract that, I just get the product of two one-point resolvents, and that we already know. So this is why we do this definition, and we call this trace 1 over P1 minus h, trace 1 over P2 minus h connected. And then, of course, you can also define higher order connected resolvents, which I will not do. It's in the notes, we won't need them. So, because we expect factorization at infinity. Now, there's one more object that I would like to introduce. Of course, we also assume that W1, 2 has a genus expansion. The reason I state that is because then I hope it will be clear once we have this equation to insert all these expansions, and then we get an expansion of order 0, an expansion of order 1 over n squared, etc., which we have to solve one by one. So the last object that we need is the so-called loop insertion operator. Well, it's a bit like a functional derivative with respect to the
potential J1 to infinity J over P J plus 1 J. Now why do I insert this object? Well, because of the following two relations. Plus okay, so well, you notice here that we didn't introduce a source for the constant term. So we start with a coupling J1 h to the power 1. We don't have a constant term for various reasons, and that's why I have to add this 1 over p term here. But otherwise, it's clear. I mean, I differentiate the free energy with respect to this potential. So then, well, you just write the free energy again as ln z over n squared. Then you differentiate this. 1 n will cancel, and then this operator here will generate moments like here, and then you can sum them up and you get the geometric series. I mean, there's nothing more in this calculation, just that this term here is missing in the geometric series. There's a second relation like this, so we can also have W1, 2, P1, P2, and in fact the higher order connected resolvent, so k-point resolvent, we get by successive differentiation. They are all defined by connected correlation functions. I will not give details because we will not compute them specifically. So our goal is clear. Compute WG of P for FG successively. So I will have to come up with an equation that we can solve iteratively, or even in a closed form. That there's actually work by Reiner where he can do that in a different way. But I would like to go this road. So we go back to the partition function and do some change of variables. And we do the change of variables in a clever way, such that the change of variables will introduce this object here. That's the strategy. Okay? And then we get an equation, which is an identity that will determine the result. So, so Z should be invariant under H goes to H plus epsilon H over K. Okay, it's just a change of variables, it's an integral. This should not change. So for all one, etc., we should have that Z over the epsilon equal to 0. Okay, so now rather than doing a single change of variables like this, we do the following change of variables plus epsilon 1 over P minus H. Okay. Now this is a good thing because this will hopefully generate this object. And this is true. So this is just H plus epsilon. I made no mistake. It's in start with k plus 1. Okay. So now we have to compute the Jacobian again. don't worry, it will not be as bad as the Jacobian for the eigenvalues. Then we get an equation. So, now we claim is that this implies that dh, which is our product of independent variables, this will change to dh times 1 plus epsilon trace 1 over p minus epsilon square. And that also the trace v of h, and that's all we have in the partition function, right? And we have that is h e to the minus n trace v of h. So we have to change look how this changes and how this changes, and then we get an equation. So this will change to trace v of h plus epsilon trace 1 over p minus h v prime of h, and v prime is just, well, v is, well, I think it's clear, no? I mean, you just differentiate like a polynomial, okay, and then you put in an argument, which is a matrix. Okay, I think this is probably easier. If you just do the change of variables, well, you just Taylor expand the potential, right? That's what you get from the Taylor expansion, and then you take the trace. This is a little bit more difficult, but I think I give this to you as an exercise. I mean, it's not so difficult. You just say that these are your old variables, hij, and then you differentiate your new variables in this form. So you just write out this as h times. And then your differentiation, I mean, these will all be contracted, will give you, of course, so just dh ij over dh this will give deltas. Okay, so you will contract one of the h's. And then to compute the Jacobian, well, you have to see how these indices then will be contracted. And, so when you set all these deltas in, you see that this term here, you have to choose delta ik, delta jl. Okay, that will give the 1 here. And then the delta ik, maybe you can read this, j k l, the delta kl in here will make that through the differentiation, these products will split into 2 traces, and that will give this term. Okay, so now let's plug this all in here, differentiate by epsilon, and see what we get for our equation. And let's divide also by z so that we get expectation values. Okay, so we get the following equation. So this is then, well, first of all, from this term, from this differentiation, we get this expectation value. I think it's clear. Square. And then we get a term from this one here, and that is expressed with the -1, the minus n. Trace okay, and let's also divide that by n square. Okay. Now,
this equation here, as I will show later, this is equivalent to the 0-0 constraint, and you can use that. Where this is given by some second order differential operator in the I will give an explicit form. This will satisfy the Gernot algebra. So it's a different realization of this else. But I don't want to lose the thread about deriving the loop equation, so let me postpone that to much later. Just want to mention it because we talked about informal symmetry today. Okay, so this is clearly an equation that contains somehow this resolvent operator, but I still want to massage this equation a bit, that we see that this is an equation how we that we can solve. Actually, you will have to remember how to solve quadratic equations, not much more, and some complex analysis that is maybe more advanced. Okay, so let us first look at this term here. Now, what I would like to use is that we had spectral density, and that we could write WP as an integral to lambda rho of lambda P minus lambda. Okay, now we will make an expansion around n equals infinity. And we assume that the eigenvalues of our matrix model will condense on a support sigma of rho that should be given by, well, at least a collection of intervals, so it should give a compact set. And in the simplest case, so it could be like this, so the eigenvalues on these two intervals. And we will actually go for the simplest solution that sigma is condensing on one interval, like for the semicircle. Remember, I mean, the larger limit did this numeric experiment. I don't know if some of you did that with MATLAB or so. That for large n, rescaling things properly, the eigenvalues all lay on one interval. Now, if we switch on higher order couplings, we can hope that this will not change. Just the form of rho will change. So let's suppose this happens. And then we will self-consistently make an expansion. So let's look at this here. Okay. So 1, 1, n. Shapes. 200h prime. So let's write this as, now we say we expand around n equals infinity, so this integral will run over the support, so the set where the density is non-zero. Other than that, we don't make assumptions. So lambda, rho of lambda, prime lambda, minus lambda. So now if you pick a point lambda here, that will be somewhere inside here. Maybe let me bigger. So let's say this is lambda. Then I can of course write this. This is a polynomial, and this is a pole at P. Now P is the argument of the resolvent, so P should be somewhere in the complex plane, okay? Because we said the resolvent that was is written here, this is only defined when P is not inside the interval. Otherwise we integrate over pole, and that we have to avoid. So P is okay. So now you have to recall Cauchy's integration formula. So we will write this as a complex contour integral integrated over a contour containing a pole, and that gives the function at the pole. Okay? So this is just integral the omega 2 pi r over some contour that I will draw in a moment. Okay, so I mean this, I think you remember, this gives this. Well, you have a function, you integrate all contour that contains a pole, you get a function. Okay. So this contour should contain lambda. Now, I would like to do that for all lambda, so I should better ensure that the contour contains all poles over which I integrate. So let's choose the contour like this, and you have to make it run counterclockwise to get a positive sign. Okay, so now I can, if everything is nice, I can exchange the two integrals. And what I get is the following. Well, I get an integral over the density of a rho over this. Well, this we have seen. This is just the result. Times the prime of omega over p minus omega. Okay? So this is one ingredient in this equation. And the other ingredient, well, we just write it out. We just write out the definition of what was the connected two-point function. So, maybe I can say what that was here. So, well, you remember the two-point function was the connected part, so that was this minus the product. Okay, so in other words, if you bring this over, this is equal to p square plus 1 over n square. You remember in the connected part, in the definition, we did not have this term. W p p. Okay. This minus the factorized part is equal to that. Okay, that was the definition. Now this we can also write in a more fancy way. We can also use here that this is v p of w. So now if we plug everything in and put everything together, let's put this on the left-hand side. We have the following equation. Omega divided by p minus omega is equal to down to p squared plus 1 over n squared dv of p w. This is the loop equation, as I think it was first derived by Yuri Marchenko in 1999 for general potential. The story goes back further. I think the first person who did these was Sasha Mikhail. You probably know much better Giovanni than I do. Okay, so Marchenko. So what we want to do now, we want to solve this equation iterative. So basically what we will do, we will put in the genus expansion here, here, and here, and then do the solution first for genus 0. Now this object here is really complicated, but it's suppressed by 1 over n squared, which is nice. So for this we will get, so for genus 0, we only need this, and this is a planar, this equation. And well, you see almost a quadratic equation. Okay, we just have to massage it a little bit using complex analysis to get the solution. And I think we still have time to do that. So the first step we need to do is we need to massage this object here a little bit. And what we will need for that is the fact that we use that resolvent, which is what, let me write it again. The leading order term when the argument becomes very large is 1 over 1 omega. Okay, just take simple trace of 1 is 1 is n, so that cancels n. So it is convenient actually to look at infinity and use these expansions all the time. So let me make a drawing maybe. Well, it's still there, but I maybe need some more space. Okay, so here we have the eigenvalues sitting. Here we have our contour. Then we have our P here. And then far out we have infinity. Okay, so maybe it's good to convince yourself or remind yourself again how you can represent the complex plane by projecting onto the sphere. So well, there are several ways to do that. One is to put the origin here, and then the points get projected. So this point gets projected where this radius hits the sphere. Okay? So this is the point infinity. Okay? So we have our cut here. That's where the resolvent is not defined. Then we have our point P, and then we have infinity. So what we will do now is we will pull this surface, this contour, to infinity. When we do that, we get a contribution from this pole that is here in the integral, and we get a contribution. So if we pull this, now you think that as a rubber ribbon on the sphere. Okay, so you pull it up, or you cannot pull it up because the P will sit here somewhere. So you have to split your contour into two. So you get a contour here, and then you get a contour here. You want infinity. Okay, so this goes this way, and then this way. Okay. You see the geometry? So I mean, it's not difficult. So let's do that now in the integral. Okay. So what we will get is, well, we will get a contribution from the pole. Then we use again the Cauchy integration theorem, and then we get a contribution at infinity. Okay, so let's call this integral I. So I is let's call this contour CP, that is a whole infinity at P, and the contour at infinity we'll call C infinity. Okay, so we get okay, I've now taken the planar limit. So when we put in our heads, we put in the genus expansion. So obviously the leading order is W0. So that's what we have. And we are also in a way lucky because the behavior of the resolvent like this is not only shared by the whole genus expansion but also the zero, because this is order 1. So this is clearly a contribution to the planar result. Okay, so that's a contribution from the contour ground pole. Of course, this will give just p prime p times w naught of p, and then we have the contribution at infinity, c infinity, e omega. Okay, so, and this is equal to square. So see, it's a quadratic equation. Not quite, because here we still have some implicit dependence on W naught, but let's ignore that for the time being. So the solution is then obviously following. We have two solutions. And then we have here plus 4 this integral over c infinity. Okay, let me abbreviate that. Okay. Now, there are two things that have to be said. We are in the complex plane, and this object here, the resolvent, is not defined along this interval here. Now we expect from the density being a semicircle, so just being the square root here along this support, that we will have to consider square root cuts in the complex plane. And you know the square root is not a unique function, so we have to pick the branch. So the branch I will pick is that this will be a polynomial in P. And I will pick that this, so if this has a degree, well, the degree is actually, as one can convince oneself, this is the highest degree. So if V has a degree D, then this has a degree D minus 1 squared, so times 2. And I will pick the branch that if I pull out the highest order in P, that I get a plus sign here at infinity. So then I need to satisfy this behavior at infinity. And if I choose the branch in such a way, I will have to choose the minus sign here so that this polynomial cancels this one, because this is a polynomial. We want it for P large. The first term is 1 over P. Okay? So choice of branches are such, we pick the minus sign. Now, so choice minus branch. Okay, now we are almost done with this calculation. We just still have to massage what is here under the integral. And so what we will do, we will make an ansatz how this will look like. So our ansatz will be that, okay, it's a polynomial. That's of course the fundamental theorem of algebra, saying that every polynomial can be factorized. And we will assume that this has many double zeros except a finite number, and the finite number we have to keep under V. And the simplest ansatz is actually the following. Now in this ansatz, what we still have to determine so remains determine L of P and A and B as functions of the couplings G, J, and V. If that is done, then we are done. This is the simplest ansatz, and it corresponds, if you like, to potentials where all the eigenvalues sit in one minimum. And basically, yesterday we had this Coulomb gas interpretation. We saw that the eigenvalues are confined in a potential. They also repel each other through the logarithmic interaction, but for large n, this will lead to the fact that they will live on a certain blob. Now, of course, you can imagine that you can make also potential, beloved Mexican head potential, and that then can happen that this eigenvalue will condense maybe in two intervals. So then we will have to modify our ansatz, and I will come to that in a moment, but let us first, or maybe I write it down, so it's clear. So this is called one-cut ansatz, or one support, because one cut, this is a function in the complex plane, this is a polynomial, if this is a polynomial, it has a square root, a branch cut of this type, and two cut would be as follows. Okay, let's call this M twiddle, because it's a different thing. P minus 1 to 4, 2 minus n. And if the potential allows more wells, then you can have more dimension. Okay, now let's count. This was a polynomial under the square root of degree 2d minus 1. Now in this case, we have pulled out 2. So we can write this like this. I think, yes. So the 2 we will leave under the square root, and the rest we will pull out. So then this will be of degree p minus 2. So for Gaussian potential, it's of degree 0, and then this is what we expect. Because, okay, I should have explained this maybe. This part here will give the spectrum density. Okay. Now here, the degree because of this will be of d minus. So let's determine m of p. Again, I will play this game that this vanishes like 1 over omega at infinity. So let's write what it is. M of p is what? P prime minus 2 w0 p divided by the square root p minus a p minus a.
Sorry, I don't get one point.
Yes.
Say the function with 2 cuts is corresponding to 2 minima, degrees of 2 minima.
Yes.
Okay.
Rough, yes. And if we have more minima, we may have more endpoints, and then we may have to look at the question which of these ansätze has the lowest free energy, etc. Okay, so well, here I just solved this equation for m of p. Okay, this is nothing further. But we also know that m of p should be a polynomial, so we can also write m of p as follows. As you see, I do a lot of Cauchy this time. Okay, it's a polynomial, so I can write it as an integral of a pole.
then this pole I can pull to infinity, and then insert this here. So this is equal to infinity d omega pi I d prime omega minus t square root omega minus a omega minus b. And then I have minus, well, let's write it down. C infinity d omega pi I 0 omega divided by omega minus t, and then omega minus a omega minus b. Now, I know that this behaves like 1 over omega. Then this here I can expand, so I can get 1 power from here, and then 1 power from here, 1 minus p over omega minus 1, 1 minus a over omega minus 1 half, 1 minus b over omega minus 1 half. Then I have to expand all this stuff, but hey, wait, we have already third order pole here, but we know that C infinity d omega over 2 pi I 1 over omega k will just give delta k1. Just by making a map, omega goes to 1 over omega prime. You go from the infinity to the origin, and at the origin you know how to calculate these things. Or you just look here and it's the same. And the Cauchy's integral theorem just tells you if you have a 1 here, you just pick the pole of order 1. If you would have a function here, you would get, for k larger than 1, you would get derivatives of this function, but because this is 1 bit. So this is gone. So now m only depends on v, and this is something I still want to write down before finishing. So so m we have determined. Okay, so we have this is b, this we know, we have the square root. And then as a last trick, we can also write this as prime of p as contra integral cp. Okay, and then we see that okay, well, this is a square root cut, but this only encircles the point. This is C. And then we have the infinite one. And of course now you see that this term looks exactly as this term times this. So we have the two integrals that can be combined. So and then we have down to 0 1 half. You just pull the contours now back together here. And then we have the square root here, p minus a, p minus b, omega minus a, omega minus b. This is the general solution for the leading order resolvent for arbitrary potential. The only thing that we still need to do is we still need to determine what A and B is in terms of the, but otherwise this is very general. And I think in the next lesson I will fix how these cropping constants, how these endpoints are given by the coupling constant, and then we will do examples like, well, first of all, we do the Gaussian to check that really the semicircle that we have seen but not proven comes out. Then we do an example for quartic. Then we can see if we do the quartic, we can tune our couplings so that we get a critical behavior, so that the density vanishes here like 3/2. So then we can play. Okay? But I think for today,